Sulagna is a very passionate JavaScript developer. She also leads React Kolkata. She's coming from the city of joy. So can we have a round of applause again for Sulagna? Come on, everyone, louder.
So thanks a lot. Thanks for this warm welcome. And I'm not going to bore you with another like who am I stuff. Everything is written in here. I'm Sulagna. I work at Stockedge, and I'm also a lead of React Kolkata. So I was about to have a talk on this topic, Web API, but then I thought that no, I'm going to talk about something else today, not on this. So when I was like some couple of hours ago, one of my friend suddenly heard that I am going to talk at React India, so they were like, okay, congratulations, you got into React India, so what is your topic? So with excitement, I was like, there is a very new API, you know, it is a update of WebSockets, and it's way more faster, way more secure. And he again become very defensive and suddenly said like, oh, again another API trying to be like, yes, I'm the best and all this kind of stuffs. And we started, I also defending my stand, he's also defending his stand, and then suddenly he stopped messaging. And I was like, okay, finally he understood that I'm right. But then I was like, yeah, you finally understood, right? So no, my data pack got over. So for that reason, I had to switch from mobile network to Wi-Fi. And that's why this delay. And do you know what I did? I smiled. Because that is the very thing I was trying to explain him all along. And okay, fine. How many of you are curious that why I smile and why I think that this has become my winning point? Okay, if nobody, I will still talk about that because that I have prepared in my mind. So to understand why this became my winning point, we have to go a little bit back and try to understand how data flow through, when we have a data, it goes through a journey. And we all, okay, again this issue, just a second. Yep. We all know these things, right? It is very much, the teacher bothered us with OSI model and all this kind of stuff. We hated it. At least me, I hated it very much. But yes, surprisingly, I find it very interesting from this year. So data goes through a journey. Based on the OSI or the TCP IP model, the number of layers may differ, but the overall flow is same. First, you type the message, it goes to the application layer. From there, it goes to the transport layer, then the internet layer, then the internet network interface layer, and from there, through the Wi-Fi or the provider, it goes to my friend's chat box. Okay? But like in each of this layer, there is a certain protocol or rules need to be followed. If we think about the application, there is HTTP as I'm talking about a chat application. So I'm considering when I type the data for the application layer, it is using HTTPS or HTTP, and it's a real-time application. So considering WebSocket as well. In the transport layer, this is again a chat application. So data needs to be completely like 100% and guaranteed delivery to be assured. So for that, I'm using TCP there. Then after that, the internet is IPv4 or IPv6. Then the network interface layer. Then through the internet provider, it goes to my friend's chat application, as I said. Now, till here, everything is fine. And another important thing is, as I am using HTTP, and HTTP's current version I'm considering, that is HTTP 2. So it has the capability of multiplexing. So what is this fancy term multiplexing? Means under one TCP connection, it can generate multiple of streams. That was not possible in HTTP 1.1 version. So when they upgraded, so in HTTP 2, they gave the flexibility of multiplexing. So the application layer has the multiplexing facility. So now, up till this, we have the like, again, like the data goes through this layers and all. So this is completely fine, right? Everybody understood up to this part? Right? Barabar? Okay. So from up to this, it's okay. Okay, this is not okay. Every time I have to go here and change. So now next thing is how TCP understands that the data has come and how it identifies. So problem gets started, as I said, the data is flowing and everything, but the problem gets started when my friend switch his network, right? But why the problem gets started? Now TCP does one thing. TCP identifies the data with the 4 tuple. The 4 tuple is source IP, source port, destination IP, and the destination port. It uses this tuple to understand the session management, and the data is, the connection is coming from where, and all this kind of stuffs. Now, when the packet gets to my friend's network, so what it does, the OS layer checks these 4 tuples. It observes these 4 tuples and looks for its corresponding session state, which is stored in transport control block, also known as TCB. It's a data structure that it internally uses. It is actually the heart of this entire TCP reliability and all this guaranteed data deliveries thing. So it has all the information it stores, like the sequence number, the acknowledgement number, for congestion control, the window size. This all information gets stored in here. Now, just a second. Now, when the OS get this 4 tuple and it checks internally that if it has any match for this 4 tuple or not. If it's fine, it's okay. It will welcome the data like, yes, you are welcome. But if it's not find any perfect match for the tuple, all it will do is that, no, you are not welcome. You got invalidated. I don't know you. That's it. Now think about the scenario. How many times a day we switch a network? And every time this happens internally. And we don't even know. All we are thinking that it is just getting a bit delayed. The messages just we are receiving a bit delayed. But internally the TCP got broke. And everything got messed up. And this is not ending here. This is just getting started. Next is, as I said, I'm actually saying it multiple number of times, that TCP provides guaranteed and ordered delivery. How it does internally. So what it does, it uses a byte-based sequence number. Means, and this is also global. I'm explaining it a bit later. So it uses a byte-based sequence number. So let's think that the data is coming, and in there some byte, like from 100 to 200, as in for an example, that particular chunk got missing, or it's getting a bit delayed. It's getting delivered a bit delayed. So every other chunk after that 100 to 200 has to wait for that 100 to 200 section or segment. And this is actually a huge flaw. Just think about how many number of data has to wait for that particular chunk to arrive. Okay, and this is known as, in computer networking, head of the line blocking. Let me go, and this is the MDN definition of what is head of the line blocking. So head of the line blocking is a computer networking term that refers to a performance bottleneck that occurs when a queue of packets is held up by the first packet in the queue, even though other packets in the queue could be processed. Means, as I said, I'm not again repeating the same things. And this got even much worsened due to HTTP2's multiplexing. Why? Just think about this. Under the one TCP connection, it can generate multiple number of streams. And let's think about in the stream A, that package got missing, that 100 to 200 segment got missing in stream A. So for stream A's 100 to 200 missing packet, every other streams after stream A, stream B, stream C, stream D, everybody has to wait for that particular segment to be arrived. And this is like another level of huge flaw. And this is, we call it the transport layer head of the line blocking. HTTP2 exactly solved this issue in its application layer. The application layer head of the line blocking it solved in HTTP2, HTTPS version 2. But in the transport layer, it is yet to be fixed. And another thing, the head of the line blocking is happening, as I mentioned, one term, global, because everything, the sequence number is getting assigned globally. Stream A, stream B, stream C, stream D, and there the particular segment is missing, so everybody has to wait for that particular stream. So this goes like another is head of the line blocking. Next is coming is TCP's handshaking process. I think many of you have the idea of TCP's famous three-way handshaking, where it will send flag from the server, the client to server, with the synchronous flag, then the acknowledgement the server will send to the client, again the acknowledgement that client will send to the server. And after this, another handshaking happens, that is the TLS 1.3 handshaking, where the again client will say hello to the server, server will again say yes, hello from the server, and then it will finish. And then the original data original data will start getting sent. Okay, so to send that initial data, it has to do 2 handshakings, and this is known as 2 RTTs or 2 round trip times. So for one, just for the initial data to be sent, it has to wait for 2 RTTs. And in the good network, it's not be a big issue, but when the network is not that good, in that kind of scenario, it is also a kind of performance issue it can give. So yes, I am talking about a lot of problems. Problems, and problems. So is there any solution? Well, if there is a problem, there is a solution, I believe. And sometimes the solution is itself inside the problem. Can you remember from which part all the problems get started? My friend switched the network, its source IP and source port got changed, and TCP broke. Now, one thing we cannot ask the user that do not change your network during a conversation. Of course, we cannot say that. So we have to think about a solution where even though the tuples or the IP or port got changed, the connection will survive. The server will not say like, no, I don't know you because your IP got changed. Now, you are invalid. I will discard you. So if we can provide some kind of system, some kind of protocols that can handle this, the problem is solved, right, basically? So is there any existing protocol before like getting started with something new? Is there any existing thing that we already have? Yes. WebSockets is, I'm talking about a protocol or anything. WebSocket is of course a protocol, but it's an application layer protocol, not something in the transport layer. How WebSocket gets started, you have the HTTP connections. First, it will connect with the HTTP streams, and those HTTP streams get upgraded to WebSocket, right? When you are doing the handshaking with the client and the server. So it is not actually the problem with the application layer. It is something inside Dipper. If you go to the transport layer, the problem is getting started from there. If you still have some kind of understanding issue, like let me just finish the entire talk first, then of course I would love to explain myself in a big Dipper. So what I was saying, is there any kind of protocol we already have? UDP. UDP is connectionless. All UDP does is fire and forget. Means it will not take the responsibility of if the data gets sent 100% in an ordered or guaranteed delivery. All it will say like, okay, I have the data, I will fire it, and I will not take the responsibility if get delivered perfectly or not. For this reason, it is way more faster, but yes, with the cost of no guarantee, no reliability. But it solves one thing that we were missing in the TCP, that is, it will, even if the IP or port get changed, it will not cut off or it will not ask for again a handshaking. So if we can think in both the protocols, the TCP and UDP, it has something good, something bad, or a con, I rather say. Something good is reliability that TCP provides and connectionlessness like UDP provide. So can we create something that have the goodness of this both, that reliability like TCP and connectionlessness like UDP? So from there, QUIC is born. QUIC is a modern transport layer protocol built on the top of UDP. You can think it as of an encapsulation layer over UDP. It delivers speed and resilience of UDP with reliability and security of TCP. It is created by Google in 2012, and after that, the IETF, its standard came around 2018, I guess. And this QUIC solve all the issues that we were actually facing in the TCP layer. Let me go through them one by one and how it is solving each one of them. First, what the issue is, think about the network migration. My friends switched the network and the TCP got broke internally. Now, what QUIC does differently, instead of relying on the IP or port, it generated a connection ID, arbitrary number that each the client and the server will generate. And when the handshaking will first happen, both of them, the client and the server, will show each other its connection ID, and after that the data will start getting sent. So as it is depending on a connection ID which is has no connection with the IP or port, so even the IP or port gets changed in between a conversation or in between the data is getting exchanged, so it will not affect the retransmission, or it will not break internally. First thing. Second is head of the line blocking. That, as this is another major issue from TCP. So how it solves head of the line blocking? It introduces multiplexing in the transport layer. We have the multiplexing in the application layer using HTTP2 stream, but we don't have that, as I said, in the transport layer. So it introduces multiplexing in the transport layer. So now what will happen? Stream A, stream B, everything will get transmitted separately and simultaneously. Next is another important is how it solves as it is depending on UDP, how it's solving the reliability and guaranteed transmission. So for that, it is depending on two important things. That is, one is packet number and another is stream ID and stream offset. So what is packet number? Packet number is every data that it is getting, it will bind it or package it with a packet ID and it will send. Okay. So this packet ID will be for checking if all the data has arrived or not for this purpose. And the stream ID and the offset is inside a particular stream. As I said, it is introduce multiplexing. So inside a particular stream, a packet is belong at which stream and under which segment. As I said, there will be some 100 to 200 example I'm again saying. So that 100 to 200 will be placed at which section. That decides the offset. So stream ID and stream offset is being used for that reason. So this is also a very important thing, that it is actually helping in the head of the line blocking elimination process as well. So together everything, TCP actually, the QUIC actually solves this head of the line blocking, provides the reliability and guaranteed delivery, and it survives the network migration. Next is, another is, this is the QUIC provides encryption that TCP doesn't have. TCP only, is by default give the encryption to the data, only the version ID and the connection ID, except both of them. everything in the data part, whatever is getting transmitted, is encrypted with the TLS. That, as you can see it from the data, the image, that only follow the more darker colors. So this packet number, type, stream IDs, everything is getting encrypted in QUIC, but just only that data section is getting encrypted in TCP. So encryption-wise, security-wise, it has also provided a lot of good features. Next, another important thing QUIC solved is the handshaking. As I said, that initially when it does the handshaking, it shows the connection ID. So what it does, it merged both the handshaking that we had in TCP. One TCP is three-way handshaking and TLS handshaking. So both the handshaking, it merged into one, and what it does with the TLS handshaking, it will just send the connection ID, and the entire handshaking process from 2 RTT, it got reduced to 1 RTT. As you can say that just the client is sending first handshake initiated, then the server acknowledge, then the handshaking part is done. So from 2 RTTs, it got reduced to 1 RTT. This is another huge improvement that QUIC did. And this is just a image that gives you better understanding how they are actually working. So and another, I forgot to mention that when this 1 RTT is happening, for the retransmission or for repeated data sending, like the first handshake is done, and after that the next handshake will made. So there it is actually taking 0 RTT. So no again handshaking needs to be done. That is another improvement. So as I was actually saying a lot, and everything got started from WebSockets. So all WebSockets, I said, the internally it is using TCP, is using HTTP2, and this TCP and HTTP2 got upgraded to QUIC and HTTP3. So now we need an API or a layer that will help this WebSocket to upgrade, and that API is WebTransport. And as I have said it here, that WebSocket is TCP's real-time hero, so WebTransport is QUIC's supercharged successor. Now what is this? Okay, it's working. What is this WebTransport? From the, if you go with the MDN definition, WebTransport API provides a modern update to WebSockets, as I said, transmitting data between client and server. As WebSocket was already doing it, WebTransport is also following these standards from the client to server. So the client and the server needs to be there, and it is using HTTP3. WebSocket was using HTTP2, it is using HTTP3. WebTransport provides support for multiple streams, as I said, multiplexing, unidirectional streams, and out-of-order delivery means any package can, no needs to be ordered delivery that after first package, the next package needs to come. It can come at any order, and it will, inside there are logics which will make them in order. And another beautiful thing WebTransport did, it has both the feature of reliable transport with the streams, that is we did in TCPs, and unreliable transport via UDP-like datagrams. So now it can give you the feature of both TCP and UDP, which WebSocket had previously missed, and WebSocket don't have the UDP-like features or datagram sending. It has only the streams or reliable transmission. So this is a simple, like the initial connection, how it getting started. So I'm just going with the code. So this is the code of, all you have to do is pass the URL through the WebTransport API, And when the transport is ready, means the handshaking is done, and then you can use this API. With the WebTransport.close, the connection will be closed. And as I said, these are the things, the reliable transport with stream. Let me quickly go with the code. It is using create bidirectional streams for the reliable part, and with the writable, it has both the get writer, writable for the writing part and readable to read the streams. So it has both. So I have used here the writable only, writable.getWriter, and unreliable transport with datagrams. That is just, this is the syntax like transport.datagrams, and this is for also the writable stream, UDP, writable datagrams rather, I would say. And datagram.write, you can write whatever or want to encode in the data. So this is a very brief definition. Now I will go with the coding part. I have prepared a demo where this is the server URL that I have, and this demo has the very basic things like it will connect, and when it will do the logs, and WebTransport has a feature of getting status. So it will show the status like how many package has dropped and what is the RTT timing, and this kind of stuffs will be shown in here. So I'm just doing a connect, and yeah, byte send 0, of course, packet lost 8, both support, this is like the streams and datagrams. Now here is the log, that initial stat fetched, and the connection is established. Now if I like say hi sent datagram, datagram sent 8 bytes, status unreliable, and if I go and connect for the TCP like streams and like hello sent on streams, that is, this is the reliable section. So this is a basic code. If you are interested, I don't have much time. If you are interested, you can come and connect. I can give you the access of the code. Just a second, the connection get lost. Connection is lost, my bad. I think it's due to the network or anything. So this is the demo part. I think the connection is lost. Okay, yeah. So this is the choice is clear. As I said, the WebSocket versus WebTransport. Already I have said that WebSocket is based on HTTP2 or HTTP1 over TCP. WebTransport is giving HTTP3 over QUIC. And the resilience, of course, it uses the connection ID, so it supports network migration, unlike WebSockets. And head of the line issue got solved in WebTransport. That was a major issue in WebSockets. Latency-wise, as whatever the TCPs, the false TCP had, everything got inherited into WebSockets, and whatever the goodness the QUIC and HTTP3 has, that is comes inherited by WebTransport. So I think the choice is very much clear. So I'm just quickly wrapping up as the time is up. So this is the new era of real-time React. As now, as I said, it is using, the WebTransport can handle the network migration. So it can actually, let's think about a collaborative app where suddenly you switch the network and suddenly everything is getting stuttered. So that is not going to happen now because it is using a connection ID. It will survive the network switch. Head of the line blocking got eliminated, so no streams need to wait for another stream to be arrived. Everything has its own issue. If one chunk getting missed in from one stream, not other streams will be suffered for that. And in WebTransport, it has support from the real-time unreliable like datagram support like UDP. So we can use the them in the multiplayer gaming and this kind of things where the speed is the main motto, and of course the time to interaction, it get cut down from 2 RTTs handshake to 1 RTT or 0 RTT for the retransmission. So yes, this is way more faster now. So yeah, the final verdict is here. I would of course suggest that start experimenting with WebTransport. It is easy to use, as you can see in the code as well. It's not very complex to start with. And if you have any query, of course you can ask, or I am there all the time, and after even this conference. So you can ask me, you can connect me on the LinkedIn, and if you have any question, you can ask me there. If you want to talk more about the QUIC or this web transport thing, of course, I would love to connect and I would love to talk with you all. So thank you.
React India.